Higgs boson's the elusive particle or field that hasn't yet been discovered, or it might have just been discovered, that's there to give everything else in the universe mass. We're made of massive particles. If we weren't made of massive particles, we'd fly around at the speed of light. Some people would like that, but you'd never join together to form bodies again. So it's very important that we've got masses. But different particles have got different masses. You know, if you just think of the standard particles in the universe, the electron, for example, and say the quarks, the top quark, there's a difference of about a factor of 350,000 between the mass of the electron and the mass of the top quark. And yet those are in the same family of particles that make up the standard model. And why? And why is it that some forces in the universe are long range, they're infinite, like the electromagnetism stretches right across the universe, but the weak force only acts within a nucleus? It's, you know, why a neutron decays and why we have radioactive decay, why does the sun burn? And the particles which give me those forces are the bosons. For electromagnetism, it's the photon, and that's a massless particle. For the weak interaction, it's the W vector boson. That's a massive particle. And nobody knew how to give these particles the mass. Why would the photon be massless and the gauge particles be massive? And that's what the Higgs particle was introduced to do. It was to complete the picture of the standard model by developing a mechanism to give particles a mass.
How does the Higgs boson do it under the theory? Is it kind of like this passenger that goes along with all the other particles, that goes along for the ride and weighs them down? How does the Higgs boson impart mass onto, say, an electron? Yeah,
that's a really interesting and important part of the process. In the early universe, the value that this particle has, in fact, the particle is just the end product, if you like. The big thing you talk about that particle physicists are interested in is the field. The field is the concept of this object that permeates the whole universe. It's got some expectation value, some average value. If it's non-zero, like if the electromagnetic field is non-zero, that might account for why your hair stands on end, you know, and if you've got a big static field there. If it's zero, then it could give things no mass or no charge. So the value of this field takes is very important. And in the early universe, the Higgs field, which, as you say, does come along with all the other particles, its average value is zero, which means that in the very early universe, all the particles in the universe are massless. They're flying around with no mass. But as the universe expands and cools, it goes through various things called phase transitions. And with the Higgs field in particular, as it goes through the phase transition, all the beautiful symmetries that are present for the field in the very early universe, which mean that everything is massless, some of those symmetries get broken. It's like being in a dinner table and you've got everyone's got a serviette or a piece of bread around them. And when you first look at the table, it's perfectly symmetric. But as soon as someone picks up a piece of bread, either from the right side or the left side, you've broken that symmetry, and everyone else has to follow to carry on with that pattern. And with the Higgs field, what happens is as the universe cools down, and it moves from this zero average value to some non-zero average value, the symmetries that it respected when it had zero average value, some of them get broken. They're no longer held. And in those regions where they're no longer held, those particles, they acquire a mass. And the other particles which have kept that original symmetry, they remain massless. So it's because actually that as the Higgs field goes from zero value to some non-zero value across the whole universe, then some of the particles acquire a mass and some don't. And that's the really important thing that's unique to the Higgs, and that's how it gives some particles a mass and some don't.
I won't pretend to totally understand, but the way you describe it then, you make it sound like something corrupted, something went wrong, everything was fine, and then as the universe cooled, something broke.
Yeah. Breaking of symmetries is absolutely vital for our existence. It's sort of counterintuitive. Almost at every level in our universe, that when we think of it in terms of particles, you need to break some beautiful symmetry that's been there at some earlier stage in order for something interesting to happen. Another example is in the very early universe, we think that the universe was beautifully homogeneous and isotropic. There was no unique place to be. All particles will have been evenly distributed. And if that's the case, then gravity could never act to cause things to collapse together. Because if everything was beautifully symmetric, so every particle was the same distance away from every other particle, gravity wouldn't know which one to actually pull on more than any other. So what's needed is some way of just breaking that beautiful distribution of particles. Some perturbation is required to break that symmetry. Then gravity can start pulling things around the particle that's been pushed further than every other particle. And that leads to structures. And the same thing's going on here with the Higgs. It's that the universe is beautifully symmetric early on, but as it cools down, you have to break that symmetry in order to generate some masses on the particle. If you don't break the symmetry, you won't generate any masses and everything would remain massless. And that's not the universe we live in, Brady. Let's talk about the fields, because the bosons, the number of particles that just reflect oscillations in the field. So I think what the more fundamental question is, how many types of Higgs field are there? And we don't know. So the simplest model, and the model that's been tested for at the LHC, assumes there's one. It's looking for the standard model Higgs particle, which is arising out of the standard model Higgs field. But if the universe, for example, is supersymmetric, if there for every particle there's a supersymmetric counterparticle, then indeed there'll be more than one Higgs field, because for every Higgs field there'll be its supersymmetric counterpart. And there's no evidence for that yet. There's only just maybe beginning to see some evidence for what you might call a standard model field. But we don't know. It depends on what the underlying theory is as to how many Higgs fields there are present. At the moment, the tests that are being done are to search for this one standard model Higgs. If it's not found, if it turns out that this tentative evidence, these excesses that are being seen disappear, as they might, then what will happen is you'll be able to say, well, we've ruled out the standard model Higgs, but then you move on. You go to the next level to try and probe it, the next most natural model, to try and see what that will give me in terms of the data. The Higgs particle is a very unstable particle, and that's part of the issue, right? If it was really stable, they'd be all out there and you'd just be able to find them. So let me give you an idea of how difficult it is to generate them. The particles that are going around I don't know the answer, by the way, so I'm kind of diverting a little bit, but you'll sort of see you'll see how few there are generated at the moment, right, by this what I'm just about to say. There are, on average, 200 million collisions a second between the protons and the going one way and the other way, so two protons smashed together. And that's happening 200 million times a second, right? The accelerator's been running for about best part of a year, 200 million collisions a second. Do you know how many Higgs have been detected? How many potentially have been detected in this data? In some of the channels, 3 Higgs. So these are small statistics, right? Because they're very difficult to produce these particles and then be guaranteed that you be fairly confident that you've seen it, because you need a lot of energy to produce them, and then they decay very rapidly, and you have to be fairly confident that you understand the decay products in order to reconstruct what you think is the Higgs in the first place. So there are many protons colliding and relatively few Higgs being produced. There's lots of other stuff being produced which is far easier to be produced.
So every single one of those protons in the Large Hadron Collider has a mass.
Yeah.
How have they got a mass unless they've got a Higgs boson along for the ride?
Right, so this is a really good question. This is the difference between the field and the particle. Okay, the field has this non-zero value nowadays. I said in the early universe it's zero value and all the particles were massless. Now everywhere in the universe it's got a non-zero value. So any particle which is coupled to the Higgs and has had its symmetry, and in the region where it's got its symmetry broken, that has picked up a value, independent of whether any particles are produced. So all around the universe, you're not producing Higgses every minute, because the Higgs is everywhere in this room, and it's coupled to the protons and the quarks inside of us, and it's giving us a mass. So what are the particles? The particles, if you like, are the fluctuations, the oscillations in that background field. So it's the equivalent of, with electromagnetism, we think of the electromagnetic field pervading the universe. Its fluctuations are the photons. The photons of light are the fluctuations in that field, and that's what the equivalent of the boson, the particles, are. They're the fluctuations in this field, and then so you can imagine you need quite a lot of energy to get the field to get excited enough to produce those bosons in the first place, and that's what the collision of the protons can do for you.
Can I make a suggestion then? Why aren't we searching for the Higgs field? Why are we searching for the particles if they're so hard to find?
Because the field is even harder. That's the problem. So we're hoping that by finding the particles, we'll actually gain some information about the field. What we would really like to know about the field is, how is it distributed? Is it really uniform everywhere? And in particular, there's a thing you associate with these fields, an energy. They've got two forms of energy. They've got a kinetic energy, an energy of movement, if you like, but they've also got a potential energy. And that potential energy is really important because when the field has, in the very early universe, the field we think is sort of concentrated around a zero value, and its potential is very high. And then all systems, all of us, right, we want to go to the lowest possible energy. We're all naturally lazy. And as the universe cools down, this effective potential changes its shape. So it goes from this parabola, if you like, which has got a minimum at zero value. So that's where it wants to be at the early universe. As the universe cools down, it forms, we think it forms what looks like a Mexican hat, right? So it goes from having the parabola being there, that minimum, that is a minimum becomes a maximum, and the minimum moves out over here somewhere, moves away, and the field rolls down to this place. But that's what we think it looks like. We don't really know what it looks like, and we would really like to gain information about the field. So ideally you would probe the field, but it's much more difficult to do that, and so what you do is you probe for the oscillations around that field and hope that will give us some information about the potential.
You said the electromagnetic field through the universe has the particle, the photon, and we live in a universe full of photons. We can't look anywhere for photons, and yet we don't see Higgs bosons associated with the Higgs field. What is it about the Higgs field that makes it so reluctant to give up its particle? It's partly because what we're finding from the LHC is that the mass of this Higgs boson is really large. Right, the mass of this boson is where, we think if it's the excess events they're seeing suggest it's about 125 GeV. That's about 125 times the mass of the proton. The photon is massless. It requires basically no energy to create it. So it's a lot easier to create the photon than it is to generate the Higgs boson. You need at least that amount of mass, energy, E equals mc squared, equivalent energy, in order to be able to generate that. And that's why you need to collide these particles together at such high energies. What was announced last week? So last week was the sort of the preliminary set of data. That's really important, right? Because there's a risk that everyone will say, this is it now, it's all done. This is a preliminary set of data, which is kind of the culmination of the initial runs that were done throughout this year, up until I think about October. Runs of the LHC, protons going around the LHC and looking at the collisions. And two groups announced results, two of the experiments, the ATLAS experiment and the CMS experiment, and both were specifically looking for signatures of the Higgs particle. And they've both seen what look like excess events. That means events above what the background would be and above what you would naturally think you should get from the standard model. And these events are at over a certain mass range, as I said, about 125 times the mass of the proton. And what they're hoping is that as more and more data is taken, the significance of these events, well, it will either grow, so they'll see more and more of these events building above the background like a volcano rising up. Or if these events are not really due to a Higgs, what they'll see over the course of the next few months is these events basically disappearing back into the background noise again. And what they'll effectively have done is ruled out all of this region of parameter space, all this mass range for the Higgs, for the standard model Higgs. As you rightly said earlier on, maybe there are other Higgs that haven't yet been found. I didn't say that, but you thought I said that, so I'll take the credit for it. Everyone seems to be talking about who's going to get a Nobel Prize if this ends up being right. Wow, a difficult one. I think it's... So, of course, it's the Higgs particle.
That's after Peter Higgs, the particle physicist in Edinburgh. This work was done back in the 1960s, okay? It actually, I was thinking about this earlier today, that it just shows you, you know, that you work on the topical things, you work on the exciting things. In the 1960s, people were working on the Standard Model. And of course, they realized there was this problem with the masses of the gauge particles, and they knew they had to come up with a mechanism to give the gauge particles masses. The Standard Model had them all massless. So not surprisingly, it wasn't just Peter Higgs working on this. There was a group, Brout and Ongley were working on it in Belgium, and then there was a group of 3 people working on it at Imperial College, including a good friend of mine, Tom Kibble. And the paper, they were working independently of each other on different aspects of it. And in fact, the papers all appeared within a few months of each other, in fact, almost a few weeks of each other. And so who do you give the credit to? I remember at one stage when it used to be called the Higgs-Kibble mechanism, and then it became the Higgs mechanism. And who knows where, I mean, it looks, of course, it looks like it's got to go to Higgs if a prize is given. But there's this crazy rule, I think, in the Nobel panel, which is it's meant to go to no more than 3 people. Well, Brout sadly died earlier this year. Historically, the order in terms of publications is Brout and Ongley, then Higgs, and then Kibble and his collaborators. And so you've potentially got Higgs and Ongley, and then you've got the 3 collaborators. I think they should abandon this 3 people maximum and give it to all 5 of them. You
mentioned that Kibble's your friend.
Yeah.
Have you spoken to him about what's been going on lately? What does he say? What does he say?
I spoke to him last week. We had a meeting, and so I said, you know, what do you think of this potential? This was before the press conference, actually, before the seminar, and he's such a modest guy and very unassuming. He says, yeah, it's very interesting. Yes, you know, we'll wait and see. And then, so I then said to him, what do you think? They've got the prize awarding committee will have a difficult decision to make, and he said, well, it'll probably be done in historical order, and that'll be Higgs and Ongley. But then he said, but Brout has died, and he went, oh well, we'll see. He knows he's done a great job. In fact, Kibble's the one that did the model most closely aligned to the Standard Model.
Was it exciting last week? If I was around here, were you guys all into it?
Yeah, it was such an exciting time, Brady. I mean, you know, you must be picking up on it, right? In particle physics, it's just great time, right, with the neutrinos, and then you've got the spherical electrons, and you've got the LHC just producing this amazing data. Yeah, we were all excited, and then it was all a bit of a damp squib for us because we went over to watch it all on a big screen, and the connection was crap, rubbish. Sorry, it was rubbish, and so we kept on seeing the screen, and the voices would disappear, and then they'd come back. The most exciting bit was our colleague Anne was following things on Twitter, and people were twittering away from the actual seminar room.
It's a thing which, if it exists, permeates the universe through the Higgs field and gives mass to everything that currently we have no theory of how it gives mass to everything. I mean, that's the only candidate that's around. Yes, it has a mass. According to the experiments, if you believe the experiments, you know it's something like 262 GeV, but who knows? I don't know. I don't know whether it exists yet. It's just a statistical blip so far. At first sight, everything should go at the speed of light, and you've got to stop things going at the speed of light. Otherwise, they're all whizzing apart, not interacting. So you have to put a term in which allows for a mass, which will slow it down a bit, so that you're quite heavy, and because of that, you don't move around too much. But if you were incredibly light, you'd be whizzing around at almost the speed of light. So something in the description at fundamental level gives things mass. And you can put it in mathematically, but you don't know whether it comes from something more fundamental. Well, I don't know really what it is. It's one of those things which is very esoteric, off the end of the maths that most people can deal with, and off the end of the maths that most theoretical physics people can deal with. It's a very rarefied, specialised bit of physics. But I can explain it by analogy with other processes, such as if you have positive and negative charges and you put on an electric field, the positive charges will move one way, the negatives the other. And you can get these going backwards and forwards like that, and that's called a plasma mode. It's just going backwards and forwards like that. And now if you put an electromagnetic field in space, the electric field goes this way, and the wave has to go perpendicular to it. So in a plasma, you find you get a coupling with an electromagnetic wave which is longitudinal in the direction of these moving particles. Now it's that idea that Phil Anderson came up with as the basis for explaining how you get a particle with mass. It is the coupling of electromagnetic waves to these charged particles inside a superconductor that gives rise to something which is analogous to a Higgs boson. And that's why he explained this might be the source of mass, and the particle physicists ignored him because he wrote it in a language which, although relativistic, wasn't their natural language. And this mathematical language is rather like me speaking to you in Japanese. You're not going to understand a word. And if you speak fluent English, you think you're talking to these guys, but they can't understand you at all. So they ignored Anderson's work for a couple of years, and then Peter Higgs picked it up, ran with it, and converted it into a proper relativistic theory of elementary particles. So it comes from plasmas in superconductors, and you can do experiments on that. Everything you can do in there works. You can find the equivalent of a Higgs boson in superconductors. That was done in 1980. But when you come to particle physics, it's a whole new ballgame. To do the experiments, you need enormous machines, such enormous machines that you keep looking for it and it's not there. Nobody knew where to look. And slowly they narrowed down the field where it could be, and now there's a whisper that it's there, just a whisper. And people get a bit excited. The newspapers say, have we found it? Have we found it? Well, no, it could be 1 in, I don't know, about 10 chance that it's not there, or 1 in 3 chance that it's not there. It's somewhere of that order. And so you can't actually say, oh, we've discovered it. You'll have to wait until the statistics improve. And then you can turn around and say to people, oh, we've made this big discovery. It is as though it's Japanese and you're speaking English, and I can't translate for you. I mean, I think that's a good analogy. You know, these high-energy physicists can't talk to low-energy physicists, can't talk to ordinary physicists, can't talk to the public. If it's found, it gives a basis for cosmology and masses of particles so that we become more secure in our ideas of what the universe is made of. If it can't be found and it's not there, then it undermines a whole range of bits of physics, not condensed matter physics, the world we live in, but we wouldn't understand the universe or how to build a model of the universe in a reliable way. So this is in some sense key to understanding the much bigger picture. We tend to believe in what's called the standard model, even though the standard model is known not to be complete. In the standard model, neutrinos have no mass. Everything goes at the same speed, the speed of light. Then we found that some neutrinos had a mass. And now we've found, or maybe found from CERN, that they go faster than the speed of light. This aspect is not in the standard model. You really want to have a firm foundation before you build out from it. It's as though you need the last part of the jigsaw or the last part of the foundations before you can build the next level on top of it. And it's that element of it, that it's a key component. And we know the standard model is wrong, but nevertheless, we'd like to check that out. Higgs is named after Peter Higgs. Now, there are several people who played a part in this discovery, but I think it was Lee who first said, oh, this is the Higgs mechanism, and it caught on because it sounds like a nice abstract thing. And the guy is very self-effacing, wouldn't push himself, and so he was a natural candidate for other people to choose him. Boson is named after an Indian physicist who wrote a letter to Einstein. His name is Bose, and if you put on at the end, it turns it into a particle. We live in a strange world. Phonon is a sound wave, phonos, turned into a particle. So boson refers to the particles that he discovered. And he wrote to Einstein and said, I've got another way of talking about light waves, photons. And Einstein ran with that, and they discovered other things which were published jointly. And so we always think of this property as associated with Satyendra Bose. First of all, we don't know very much about them, except we think we know what their energy is now. but we don't know the coupling constant, how they interact. That is, if we talk about coupling between charged particle like an electron and electric field, it depends on the electric charge, and that's a number. We don't know the numbers for the interaction with the Higgs field with anything else at all. At all. I mean, completely ignorant of all these things. We started out ignorant of the energies and of these constants, these coupling constants. And if this is the right particle, we'll know a bit about the energy. We might know a little bit about the interactions it has. But there's a whole range of things we don't know about it, if it exists.
How does not knowing things like coupling constants make it hard to find?
Well, if they were big, we would find them straight away because they would be affecting our lives enormously. If they're very weak, then they're just having a titchy little effect on everything except giving them mass. And that makes it rather difficult to measure. You know, it's a measurement problem. Now, I am as ignorant as you about these things. You go and talk to the experts about this, and they will be as ignorant as I am because you have to be one of these people working on the large... I mean, it's a small specialist gang of mechanics who build this machine and know how it works and how they're going to do it. I don't know how they do it.
Do you read the stories and the papers that come out of it? Are you even interested?
Oh, yes. But if it comes out in the press, it's like you coming to me and saying, explain this to me. And you can't find the language which will explain it simply. There was a Conservative MP, William Waldegrave, who asked for people to write 1 page of A4 to explain the Higgs boson to the public. And there was a competition and somebody won it. And you can't really do that. That's what you're asking me to do. 1 page of A4, written simply, and talk about Mrs. Thatcher moving through a party and everybody coming towards her and making a mass around. That's not it at all. You have to talk about broken gauge symmetry and different groups and all sorts of things which are too abstract for even undergraduates. We don't teach them that. It is a difficult subject for undergraduates. You need a schooling in this subject before it makes any sense. And what you read in the papers is a distillation of somebody who knows about it talking to somebody in the general public and watering it down, and then their garbled version coming out in the public. The advantage talking to you is I am giving you a garbled version and you're putting it out for the general public who won't understand it, because at bottom I don't understand it. I cannot explain it simply to the general public because it is, well, I would use the word recondite, and that means that it's so obscure that you have to go and look up the words and the meaning in a dictionary. And that is the difficulty. You have to use a mathematical language which is rather obscure in order to get to grips with it. And you have to have a mental picture. I mean, the one that's used, you'll find my colleagues love this, is a Mexican hat. Now, this is my wife's Chilean hat from Italy, from Montepulciano. And you imagine there's a potential that runs down and then has a minimum around here. Only if it were a Mexican hat, it would be completely symmetrical. And you imagine the particle comes down and oscillates in here. And then they'll talk of broken gauge symmetry, which means that it can go in any single direction around here. And this doesn't mean anything to you. And then you say it doesn't matter if you fix it and it's a broken gauge symmetry and it just oscillates this way and it's this oscillation which makes up the Higgs boson. That doesn't mean anything to you, but to people in the field, they would know roughly whether I've got it right for a start, and I'm not sure I got it right, and whether this is the right physics. And it is the oscillation in a symmetric well which has a certain symmetry which causes the Higgs boson in superconductivity, and if it's the same in high energy physics, that's it. Well, this is a paper by my old boss, in a way, P.W. Anderson.
Hang on.
This is Philip Warren Anderson, who was in charge of the theory group at the Cavendish Laboratory when I was there from 68 to 71, and he wrote me a nice reference. So I got the job here. I don't think I'd done anything particularly good. They just looked at his name and thought, well, if he thinks he's okay, we'll have him. This is the paper. It's in Physics Review, and it's in the particle physics section. He's a condensed matter theorist who worked on things like superconductivity, who explains how you can have plasmons, these positive and negative charges moving in a superconductor, leading to mass. And if you read this carefully and you're a theoretical physics person, you would understand that he actually got the essence of the Higgs problem right. I got Higgs here, if I can find it. This is 1964, Peter Higgs, Broken Symmetries. That's the paper where he comes up with a version which is written in the language of particle theorists, which is Lagrangians and covariant derivatives and all sorts of frightening mathematics. I mean, it's frightening for me because I'm not used to this language mathematically. And in it, I'll show you cited in, there's a little
That's it. I got it.
down there,
Yeah.
he cites the paper which came out 2 years earlier by P.W. Anderson. So he's building on Anderson's idea, converting it into the language of theoretical particle physics, and then showing some other clever trick which indicated there was a Higgs boson after all. So this was the first realistic model. But actually, when I say first, there were about 3 groups operating at the same time who published roughly at the same time. This is a group with Kibble. Kibble is somebody from Imperial who did some work. He published the same idea, and this is 1964. This is October. And there's another group, Englert and Brout. See, I have done a bit of trouble about this. There's Englert and Brout, which I think is June 64. It's all done within the space of a few months. And there was no internet then. You couldn't read things simultaneously. They had to be published, and they would come out slightly later. So this was all done at the same time. So these 3 groups really did the same physics at the same time, based on Anderson's stuff. Oh, well, Higgs has got his name associated with it, but that's not because he pushed himself. So it will always be known as the Higgs mechanism in the community, and it would be outrageous if he's not rewarded. But if the Higgs boson hasn't been discovered, no prizes will be awarded. So it's contingent. It depends on whether they actually see it. If they do see it, it's going to be somebody in that group, and it's going to be an awkward decision because you could choose Higgs, you could choose, well, I don't know. I don't know who you would choose else. And the other thing is, if it takes about 10 years, most of these guys will die off and they won't get a Nobel Prize at all. So it's really waiting to see who's going to be left standing when the Higgs boson is found, which is a rather sad lesson. Some people do brilliant work and die young.
This work was done in the 1960s. Why did I never hear about the Higgs boson until I was in my 30s? What's going on here? Why was this kept a secret? This is old work. And it's important because it's what gives things mass, something so crucial. That's
a very good question, but you have to understand particle physics has evolved slowly. And first off, people tried to use it for the strong interaction. It didn't work. It just didn't work. Then they tried to use it for the weak interaction. It did. And you get this funny mixing of electromagnetism and the weak interaction. You get the Z boson and all those particles. You go to the strong interaction, nobody has an idea of how to do it. And the only candidate left standing is this one. So as soon as you've moved beyond the weak interaction up to the 80s and 90s, this became the thing, the last thing standing.
The last thing standing for what?
Well, the standard model...
The last thing standing to explain mass?
No, the last thing standing in our simple-minded view that there are quarks, that there are muons and leptons and all these things, and then there's the particles, the W's and the Z's and the gluons and so forth. That's the standard model picture. And then once you've filled that all out and found the top quark, the next thing was to look for this other particle which is more energetic, going up in energy all the time. And you got the top quark and you just thought, oh, we'll go a bit more and we'll find the Higgs, and we'll go a bit more and find the, oh, go a bit more. And now they think that the bounds have come round to such an extent that it must be in a narrow window, and that's when money was spent. But I have something by Peter Higgs himself, where he quotes people way back in, well, this would be, let's see, I'm not doing this very well, am I? This is something from Ellis Gaillard Nanopoulos from 1976. And this is a quote that Higgs does from this paper. He says, we should perhaps finish with an apology and a caution. We apologise to experimentalists for having no idea what is the mass of the Higgs boson, unlike the case with charm, and for not being sure of its coupling to other particles, except that they are probably all very small. For these reasons, we do not want to encourage big experimental searches for the Higgs boson. But we do feel that people performing experiments vulnerable to the Higgs boson should know how it may turn up. So that's how they were writing in 1976. In the 80s, they'd gone through all these energies, got up to higher energies, and started to think, well, maybe we can still find it. Is science wasting money? I think
on this.
There will come a point when people will say that's enough, but I don't think that stage has been reached yet. It's clear that we will get to an energy where it's unfeasible to do it, and we're going to have other priorities in the next 10 years. Going through a session is not a good time for saying millions of pounds have got to be spent on this. But now it's up and running, we'd be foolish to stop it in the next few years.
But you said yourself, you've said, to paraphrase, that this is something that can't be understood by the layman. So what good is it to the layman? Even if you find a Higgs boson, you'll never be able to explain to us what it was. What's the good of this to the people who are paying for it, the taxpayers?
That's another very, very good question, and I don't know how to answer it. But I can tell you that people have to understand how nature behaves so that, for example, you can then measure all the protons in a body using MRI, and then that's of great benefit. But when it was at the stage that you weren't finding out how the nucleus behaved, you had no idea that that was going to come out. So doing fundamental research and understanding everything lays the groundwork so you can then build things which will be inventions. And you cannot tell where they'll turn up at all. I mean, I've told you in the past that I actually got involved in MRI and the designs because I was doing something completely different and useless, which was studying the flow of liquid through superfluid through a capillary tube, which is of no use to man or beast because when you work it out, it doesn't actually fit the experiment. So who knows what will come out of it?
What is a Higgs boson? It's what gives everything mass. It's the sort of crucial ingredient in nature that gives everything a mass, everything you see. If it wasn't for the Higgs boson, we wouldn't have this, we wouldn't have mass in the universe.
Okay, that's what a Higgs boson does.
Yeah.
What is it? What actually is it?
Well, it's a particle. It's a particle. It's also what we call a field, which means it's sort of, it permeates all regions of space. And the thing that's been discovered, of course, is the actual particle, the Higgs particle. And of course, it's, as I said, but its properties that are that it does this very nice trick of giving mass to everything around it. Can I bring my hat into this at this point? Well, this is where the Higgs lives. The Higgs lives on this hat. So, and you ask what is the Higgs particle? Well, what happens with the Higgs is it rolls down the top of the hat, down to this little bit here. And the sort of what we call a Higgs particle is the sort of excitation of it as it rolls up and down that little bit of the hat there. That's what we mean by the particle. It's like the excitation about some sort of special point, which we call a vacuum. My finger is the Higgs. So you start out, and it's in this point here. This hat is what we call the Higgs potential. It sort of controls what the Higgs doing. So, just think of the Higgs as being like a little ball on this hat, and it's rolling around, say. So at the top here, okay, it's unstable because, the excitations are unstable because if you nudge it a little bit, it's going to fall down the hat, okay? Now, that happens, it rolls down, you get a process, what we call spontaneous symmetry breaking. Then the Higgs ends up down here, okay, and then the excitations around that point here, this point at the bottom of the hill, if you like, at the bottom of the hat, those are what we call the Higgs particle. And it's the properties of the excitations around this point also give mass to everything else.
So in that analogy, where is my proton or my electron or whatever has been given mass? What's that got to do with the thing that's been given mass?
Okay, so there's something quite subtle about these excitations is that if you look, okay, the excitation's going along that direction, they can see that they're sort of seeing the slope of the potential and whatnot. But the ones that go around here, you might think, well, there's nothing special about that direction, right? And sure, you know, if you didn't have things we call gauge fields knocking around, then what would happen is there would be a massless excitation of the Higgs along this direction. Now, we don't see that in nature. So that massless mode essentially gets sort of swallowed up by what we call the gauge fields, things like the W and the Z boson, and they pick up mass by sort of eating up those degrees of freedom. That's how it works.
Do you realise how hard this is to understand for me, and how little sense this is making to me?
Well, I can give you an analogy for how the Higgs mechanism works. So the mechanism, the analogy people normally use is they say, well, imagine a room, right, I don't know, in Hollywood or something, right, and the room's empty, and you get some superstar like, I don't know, Brad Pitt walks into that room, and there's no one in the room, so he can walk about freely, there's no problem, okay? Now you go later on in the day, and the room is filled with people, okay? Let's call them Higgs people, if you like, right? Now, Brad Pitt walks into that room, and he can't so easily move about because everywhere he goes, he gets surrounded by these Higgs people who sort of want to talk to him, want to be with him, you know, want to associate themselves with him. And so, if you like, it's difficult for him to move about. It's like he's got sort of, you know, a lot of mass, if you like. That's the analogy of the Higgs mechanism, really. It's like, you know, you permeate space with this particle, so rather than being here, it's down here, and then that gives mass. Everything else sort of absorbs the mass from that.
So in the case of Brad Pitt, in that analogy, the thing that gave him mass were all the people getting in his way, hindering his movement.
Yeah.
In the case of the Higgs boson, what's giving my particle mass? What are those groupies doing that's impeding the particle?
So it's the fact that the value of the Higgs field is different here than it is here. So down here, that value, that non-trivial value of the Higgs field, it's a non-zero value of the Higgs field. So if you like, the fact that there were people in the room rather than no one in the room, that's what the particles, the other particles absorb. They absorb that fact.
Why is it called a Higgs boson?
Well, that's a good question. So obviously it's named after Peter Higgs, who is one of the authors of one of 3 papers that really proposed this mechanism. And I think that the thing that Higgs did that was sort of is probably why it bears his name, is that he was, of the 3 papers, these 3 amazing papers back in 1964, Higgs was the one that actually predicted the existence of a particle. That was what sort of made his stand out. And I can sort of read it to you, actually, what he says. This is a particle physicist's way of saying that you should be looking for a particle. He says, this is his 1964 paper, by the way, it is worth noting that an essential feature of this type of theory, which has been described in this note, is the prediction of incomplete multiplets of scalar and vector bosons. That basically translates as in, you should be looking for a particle, and that's the Higgs particle. And because he said that, he got the name, essentially.
What happened last week?
What happened last week? Well, I don't want to say that they discovered the Higgs boson, because they didn't discover it, but there was a smoking gun, shall we say. There was an announcement that there was good evidence for the Higgs having been discovered by, in particular, one of the detectors, the Atlas detector. But the evidence isn't completely compelling yet. Okay, we measure sort of how important this is through what we call sigma. So at the moment we're at about 2.3 sigma confidence level. That means we're at about 98% confident in this result. But that's not a discovery. To be a discovery, you've got to be 99.9999% confident. 5 sigma is that what we call it. We're not there yet. They think they'll be there by the middle of next year, so we'll see.
So it's seeming, I don't know, it seems likely now. What will it mean for people in your job if they give it a thumbs up?
Well, it really just confirms what we'd sort of expected. It's quite light. It's a bit lighter than we might have thought it would have been. It's certainly compatible with you know, a normal, what we call a standard model Higgs field. So it's not thrown up any shocks, I wouldn't say. What it has done, I guess, is it rules out a whole bunch of models which predict a different mass for the Higgs field. So you know, that's something that now, when you come up with a model of particle physics, you have to respect the value that we're seeing, this mass for the Higgs. That it's been discovered is, you know, a great achievement of experimental physics. You know, it's basically what the detector at CERN was built for. Okay. In terms of, from a theorist point of view, what does it change for us? Well, I guess we all believed the Higgs mechanism anyway, or most of us. We weren't really looking for alternatives. So, it's been laid down in these 3 tremendous papers from 1964, and, we're sort of bought into it. So, I guess what would have been more interesting is if they hadn't found it, right? Because then we'd be thinking, oh, right, okay, where did all this mass come from, right? There'd be a question to answer, but I guess these guys got it right. That would be the message.
One last question, and I don't know what the answer to this is, but mass is a big deal. Mass is an important thing. Everyone learns about it at school. I learned about mass at school. These papers have been around since the 60s, explaining this theory as to where mass comes from. Why had I never heard of a Higgs boson until a couple of years ago? Why was it this kind of thing? Why was it not a big deal before?
I think because they had no way of finding it. I think that's the key point. The way you'd find something like this is by smashing together, sort of heavy objects, like smashing together protons and whatnot. And, up until before they built the Large Hadron Collider at CERN, there was no way we had any hope of detecting this thing. And even now, you think of how many processes are going on in the Large Hadron Collider, 600 million per second events. And yet, I think it was only about 70 of these that actually gave a signal of the Higgs. So, even then it's remarkably rare. But prior to the building of this machine, there was no way. So the way the Higgs has appeared in this is you create, you get this collision, you create particles, which then can annihilate, and you get a series of events happening. Now, if you get enough of those, then rare stuff can happen. Okay? And what's one of the rare things that happens, that may have happened, we think, is that a Higgs particle decayed into 2 photons. And that's what we've detected. But in a way that only the Higgs would have done. So that's how we've detected it.
Why doesn't this happen spontaneously? You need massive energy for this to happen.
Yeah. I mean, we're talking about a process which has to go on at least at this energy scale of 126 GeV. It's also incredibly rare. Strengths of couplings come into the equation. So there's a lot going on there. And the trouble is, there's a lot else going on that's much more likely to happen than the Higgs event. And that's what makes it really hard.
When they announced this press conference was going to happen last week, and then there was, I don't know what was happening here because I was away. Were you watching it on the internet? Were you excited, or were you?
We did watch it on the internet, and it wasn't great because the internet connection was rubbish. Not at Nottingham, but at CERN. So we had it all hooked up onto a big screen, and the stream was just rubbish. And it's kind of ironic because the guys at CERN invented the internet, and yet the internet connection wasn't working very well. So it was a bit sort of stop-start. So I think we just sort of chatted about it afterwards rather than got too much from that. And there's a lot of people moaning about that. But, yeah, that's the way it was. Well, when they get the 5 sigma result, then there should be a Nobel Prize. I mean, there'll be one for the theorists and one for the experimentalists, and I guess it's going to have to go to the theorists first because they're so much older. And there are a lot of people that are in the mix. I mean, so Higgs obviously is one, but he's not the only one because there were these 3 tremendous papers in 64. So there's Higgs's, there's Guralnick, Hagen and Kibble, and there's Englert and Brout. So all these have got a sort of a say. Anderson as well, who had the original sort of spark of idea, I guess, back in 1962. But it was these 3 papers from 64 that finally made it more concrete and made it more calculable.
Anderson's got a Nobel Prize there, hasn't he?
He has, yeah. He has already got a Nobel Prize. He's also pretty old. But, he didn't get that on his own, so he can get another one. But there are only 3 people allowed it. So, it really is anybody's guess. They've all got a shout. I mean, they each have their own merit, each of the papers. So, if you look at them, the Englert and Brout paper, well, that came out on the 26th of June, 64. So that was the first one of this group of 3. Higgs's came out in August, in the August of that year. But what did Higgs do? Higgs predicted that actually you should be looking for a particle. And then, of course, you had the Guralnick, Hagen and Kibble paper, which came out in October of that year. And that was the most complete of these papers. Okay, so that's got merit as well. And of course, back in the day, there was no internet, there was no rapid communication like you have now. So, these were all done independently. So it's a difficult call. I'm not going to call it. But 3 of them should get it.